6.3 talks about sampling distribution and estimators. Well, the sampling distribution of a statistics is the distribution of all values of the statistics when all possible samples of the same size n are taken from the same population, typically represented as a probability distribution in the form of a table, histogram, or a formula. Here's an example. So the work is a bit more complex than the traditional. Given 3 numbered bowls, 1, 2, 3 of them, we will select 2 of them, right, with replacement, and find the mean of their numbers. So what could happen? I could, on my first, I'm going to pick 2 of them. I could pick bowl 1 to be number 1, and I could pick bowl 2 to be, oh, well, since it's with replacement, I could get number 1 again. I'm going to use a different color. I could pick number 2, or I could pick the third. Or, on my first attempt, I could have picked second bowl. Right? I could have picked my second bowl, put it back. I could have gotten the first on the second attempt, the second, or the third. Or on my first attempt, I could have picked the third bowl first. And when I put it back in and pick the second, I could pick the first, the second, or the third. Now, what's the average of those? 1 plus 1 divided by 2 is 1. 1 plus 2 divided by 2 is 1.5. 1 plus 3 divided by 2 is 2. 2 plus 1 divided by 2 is 1.5. 2 plus 2 divided by 2 is 2. 2 plus 3 divided by 2 is 2.5. 3 plus 1 divided by 2 is 2. 3 plus 2 divided by 2 is 2.5. And 3 plus 3 divided by 2 is 3. So, when they say this is the mean, and when they say, well, fill in the table, find the mean, we did B. Fill in the table below using the data from A. So this is A. What's the mean? The mean is either 1, 1.5, a 2, a 2.5, or a 3. Well, what is the frequency for 1? Well, I only see one of those. 1.5, 1, 2, 2 of those. 2, 1, 2, 3 of those. 2.5, I see 1, 2 of those. And 3, 1. The relative frequency, 1 divided by 2 divided by 3 divided by 2 divided by and 1 divided by. What's the total if I add those? That is 1, 3, 6, 7, 8, that's 9. 1 divided by 9. So each of those divided by 9. 1 divided by 9 is 0.111. 2 divided by 9 is 0.222. 3 divided by 9. Alright. Simple math. So this is 0.22 and this is 0.11. Alright. So draw a relative frequency histogram. Well, let's see. What we want 1, we want 2, no, I'm sorry, I forgot the 1.5. The 2, the 2.5, and the 3. So we're going to go ahead and see for the 1, 0.11, a little bit above 1, barely. That went a bit higher than I thought. There you go. 0.22, double that. I want them to have about the same width. And there it is. 0.33. of course, you don't need to get those to be perfect on the homework. 0.22 again. And the deal is, when you glance at this, the reason this is important, it gives you a good idea about the distribution. And if I was to ask, what does this look like? If you take the mid of those and connect them with a smooth curve, doesn't that look like a normal distribution to you? If it's a bell-shaped curve, then that is a normal distribution, not standard normal, right? And this is, of course, the relative frequency. So the deal here is, as the number of samples approach infinity, the relative frequency distribution will approach the normal distribution. So sampling distribution of means, it's the sampling distribution of the mean is the distribution of the sample means with all samples having the same size n taken from the same population. So kind of like figuring out, on average, how much does a restaurant sells per day. And you do that for 30 days. And now you're trying to figure out the average of the averages. That's kind of what you're doing. Important notes to keep in mind. You don't need to memorize those. The sample means target the value of the population mean, meaning the mean of the sample mean, we set it equal to the population mean. That's important. Again, something we're going to use all throughout in 6.4, and you'll see how that works. The distribution of the sample means tend to be normally distributed. So what do we say? The distribution tends to become closer to normal distribution when the size increase. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistics has a mean that is equal to the corresponding population mean. Well, it turns out the unbiased estimators p-hat, we're going to learn about that in chapter 7. The sample mean, the sample standard deviation. And the biased estimators would be the median. Again, you don't need to remember those. The range. And the sample standard deviation. So we're going to use that in the next section, and we'll see how that applies.